Okay, welcome back everyone. This is the second part of our lecture series on Chapter 21, Charges and Fields, and we're going to be focusing on gravitational and electric fields for this part of our discussion. But before we do that, let's just go back and review what we learned last time with charges. And so here we have two spheres that have equal mass and charge that are hanging from strings of length L. And we want to find an expression for the charge Q in terms of m, theta, L, and other constants. So the first thing to do is to isolate one of the spheres, which are in equilibrium. And because they're in equilibrium, that tells us that the net force is going to be 0. So if we can determine what the forces are on each sphere, then we should be able to proceed. So we're going to have a tension, which is going along the string, pointing away from. We're going to have mg going straight down, force of gravity, and because the spheres are charged, there's going to be an electrostatic force of repulsion. So what it looks like here is that we're going to have a component of the tension, Tx, which will balance the electric force, and we're going to have a component, Ty, which will balance the gravitational force with an angle theta up here. So that means that if F net is equal to 0, then F net x equals 0, and also F net y is equal to 0. So if F net x is equal to 0, that means that Tx is going to have to be equal to Fe, the electric force, and if F net y is equal to 0, then Ty will be equal to mg. So Tx we can write as T sine theta in this diagram, and the electric force is going to be K, Q1, Q2, but it's the same charge, so that's Q squared, over R. Now R is the distance between the charges, which if you look at the diagram is 2L sine theta, because one side here is L sine theta from here to here. So the total distance is 2L sine theta, and then that needs to get squared for KQ over R squared. Now Ty is going to be T cosine theta, and that's equal to mg. And if I call this equation 1 and equation 2, if I divide equation 1 by equation 2, my tensions will cancel out, and I will get that the tangent of the angle is KQ squared over mg times the quantity 4L squared sine squared theta, just distributing that square. And then I can solve this for the charge. I can get Q squared is equal to mg, let's put the 4L squared here first. So 4L squared mg sine squared theta tangent theta over k, and then I'm just going to take the square root to solve that for the charge. So there is my expression for the charge in terms of all the other constants. And you'll see a homework problem where you need to do a similar problem to this, but you have to work backwards to solve for the angle. And it's a very similar method, you just have to do kind of a guess and check. Okay, so the topic for this lecture is the concept of a field. Okay, so what do we mean by a force field? Well, a force field creates a force when an object is placed in it. It's a property of empty space, and what we can say is that an electric field creates an electric force on a charge placed in it. And so the electric field is created by a charge distribution. That's the most important thing to take out of this. Similarly, a gravitational field creates a gravitational force on a mass placed in it. And the gravitational field is created by a mass distribution. So it's the same concept. And in earlier chapters when we studied gravity, most of the mass distributions that we studied were either points or spheres. we didn't really look at, for example, a line of mass, but we'll be doing that with charge. So we talked about this previously, but if I was going to draw the gravitational field around the Earth, let's just go back a step. Okay, the gravitational field around the Earth, here is the Earth, and this is maybe big M. And the gravitational field we imagine by taking a mass little m and drawing the resulting force vectors at different places. And of course, if we're closer to the Earth, then we're going to have a larger value for the field. So it depends on how far we are. It also depends on how much mass the Earth has. So big M and R are factors in the gravitational field. And as a matter of fact, we can calculate the gravitational force, Fg, on a small mass, little m, in a gravitational field, g. So Fg, the force, and little g, the gravitational field, those are vectors. And we can calculate the force by noting that F equals mg. Okay? And this is important because the gravitational field G could be defined as the gravitational force per unit mass. So these are both very important statements of the same thing. So what's an equation that we can use for gravitational field calculations? Well, if the gravitational field, gotta clicked ahead of myself here. The gravitational field is the gravitational force divided by a test mass. So that's big G, little m, big M over r squared, all divided by little m. So if you remember back to chapter 13, that's what the force of gravity was, the magnitude of that. Okay, so those little m's cancel, and the value of the gravitational field is big G times the mass of the Earth over r, which is the radius of the Earth squared. And if you plug in the numbers for this, you get about 9.8 meters per second squared, or you also get 9.8 newtons per kilogram. Now this is important because this shows us that we have force over mass. Every kilogram of mass experiences 9.8 newtons of force. And so what we can say here is that the gravitational field is equal to gm over r squared r hat. Okay, so it's very important to note that this m right here, this is the mass which is causing the field. And the value in parentheses is the value of the gravitational field. It's the magnitude, if you will. And of course, the r hat signifies that it's in the radial direction. Okay, so now what I'd like you to do is take a moment and pause, open up a browser, and search for PhET charges and fields. It should run pretty easily on your computer. And take a couple minutes to explore, and then when you're done, go ahead and come on back to this video. Okay, so what are some things that we hopefully saw by exploring this PhET simulation? First of all, we can draw the electric field around a positive charge. Okay, so a positive charge would be like this, and instead of having a little m that we move around everywhere, we have a little q. And this little q is a test charge, and the test charge is always defined to be positive. Okay, so big Q, that is the charge that is creating the field, and little q is the charge that is experiencing the field. So a very similar argument to what we did with gravity. Similarly, if I do a negative charge, here's negative q, and now if I have a bunch of test charges, they will get attracted to. Okay? And remember that these test charges don't change. They're all positive and they're very small. So they're small enough that their charge doesn't affect the field that the large negative Q is creating very much. It's analogous to thinking about how much an astronaut floating around the Earth would affect the Earth's gravitational field. So basically not at all. And so that's what we want to think of with a test charge, is something that's very small and positive. Okay, so this is the electric field around a negative charge. So now let's write an equation for this. And similarly, we know, just like the gravitational force is m times little g, we can write a similar expression to say that the electric force is equal to Q times E. Now, the small charge in the electric field, that's what we're calling little q. The magnitude of the electric field, that's what E is, capital E. Okay, so that's the magnitude of E. And our equation is F equals QE. And you'll notice that this leads directly to an expression for the electric field. The electric field is defined as the electric force per unit test charge, and it has the units newtons per coulomb. Now there's other units for the electric field that we'll get to later, but this is a good start. Okay? Okay, so one thing to point out is that if we have a positive charge, then the field and the force will point the same direction. So for example, if I have a field going like this, and I have a positive Q right here, then the force will also be to the right. Contrast that with if I have a field and then I have a negative charge. It will experience a force to the left. And because the charge is negative, the force must also be negative in order to satisfy the equation F equals QE. Okay, so what equation can we use for electric field calculations? Well, similar to gravity, we had, as a reminder, G is equal to big G, big M over R squared. Similarly, the magnitude of the electric field is our constant K from earlier, Q over R squared. Now, if you want it without the magnitude, then you would just get rid of that and say that it's in the R hat direction. Okay, so we have the magnitude right there, and we have a radial direction. Okay, so for a point charge, it's KQ over R squared. Okay, we can also use E equals FE over Q. Now the limitation of this equation is that we have to have point charges or spheres. Okay, so here is our summary of the electric field. E is equal to KQ over R squared in the R hat direction, and it's also equal to Q naught over 4 pi epsilon naught R squared. Now we got to that by remembering that K is 1 over 4 pi times epsilon naught. And what that does for us is if we take the 4 pi R squared out of this, it allows us to recognize that E is equal to a constant times Q over epsilon naught. Now that constant is 1 over 4 pi R squared, depending on what R is. So at a certain location, the electric field depends on the charge and the electric constant, epsilon naught. And this is a very important result that we're going to be using in an upcoming lecture. And this got cut off a little bit, but any charge little q, which is in the electric field created by Q naught, we also wrote that as the big Q, is going to experience a force, which we can write as F equals QE. So that's just what got cut off at the bottom. Okay, So, last thing to summarize here is which way the electric field points. So the electric field is the direction that a small positive charge, so a test charge, would move if it was placed at that location. The electric field points away from positive charges and toward negative charges. So these are the big Q's that are making the field, not the test charges that you're placing in it. If you have more than one charge making a field, you do the same thing that we did last time, where you do superposition. You calculate each of the electric fields separately, and then you add them up using vector math. Okay, so that's going to be it for this presentation. Next time we're going to talk about charge distributions and how to calculate more complicated electric fields. We'll see you then.